Welcome everyone again to this third lecture of the CRM Distinguished Lecture Series in Applied Mathematics. My name is Felix Kwok. I'm part of the scientific committee for this Distinguished Lecture Series, together with Jean-Christophe Nat at McGill, Morgan Craig at Université de Montréal, and Erica Moody at McGill. It is our honor to welcome back Professor Nilima Nigam of the Department of Mathematics at Simon Fraser University. She gave a talk already on Mondays, and today is her second public talk in this series. In case you missed it, so let me give you a brief biography again of Nilima. Nilima is actually no stranger to Montreal and the CRM. After she completed her PhD at the University of Delaware and doing a postdoc at the Institute of Mathematics and its applications at University of Minnesota, she joined McGill and was a prof there for 7 years. In 2008, she was hired by Simon Fraser University as a Tier 2 Canada Research Chair in Applied Mathematics, and she was also the Associate Scientific Director of MITAX, a nonprofit research organization offering research and training programs in partnership with government, universities, and industry. Nilima's research interests are very broad. Well, the core interest is in partial differential equations and numerical analysis with applications in computational electromagnetics and spectral geometry. But she's not shy to make her math applicable to real-life applications. She has a lot of interdisciplinary projects with biological industrial applications. So for instance, she was working with it was the kinesiology and
biomedical
physiology department at Simon Fraser University. One of her projects is on modeling muscles using finite element methods. And for her many contributions, she was awarded the Kames Fields Industrial Prize in 2021, and she was elected Fellow of the Canadian Mathematics Society in 2023. On a personal note, I was very lucky to be a student at McGill when she was a prof there, and I've always enjoyed our discussions, which I find very inspiring back then and also today. One thing that really impresses me and inspires me is that, you know, she could tell us her latest research projects, and it always gets me all excited and it makes me want to work on it. So today I'm really excited to hear what she has to tell us today, and it's going to be on math that resonates. So thank you very much, Nilima.
Thank you, Felix, for that lovely introduction. Yeah, it's been such a pleasure to be out back in Montreal, and particularly to see familiar faces. It's wonderful to be here. All right, so this is an unusual talk because I'm looking at the non-mathematicians here. There are a few. There are many mathematicians, but my talk is aimed at the few, okay? So if you're a mathematician and you're going to be really irritated with some parts of my talk, that's okay. We shall survive, okay? All right. So I wanted to tell you a little bit about this area of mathematics that I feel is truly beautiful, okay? And I'll try and convince you, A, that it's pretty much everywhere you look in some form or the other, and B, that mathematically it has inspired a whole lot of the very beautiful stuff that we study. Okay, so the title, of course, is a pun, and I hope it'll make sense as we go through. So my hope is that this talk is interactive. So right here is a definition of a colloquium or a public lecture. And what it really means, going back to the roots of the word, is that it's a public conversation. So don't let me rant on. Please stop me if you have questions, and there will be audience participation required at some point. This is not a soliloquy. A soliloquy is basically a talking to oneself. Right. My somewhat overambitious talk plan is to try and describe to you what's going on in all of these pictures and many, many more. Let's see how far we get. But I start from a very, very long time ago. I'm thinking about two very old human preoccupations, math and music. And in fact, if you want to learn all about math and music, I strongly encourage you to go to the public lecture by Professor Alex Barnett, which is the next one in the series. He will be doing an amazing collection of, well, mathematical exposition and demonstrations. So what I have here on the slides is a figure showing some drums. And these are some of the oldest known human musical instruments. All right, they're like hundreds of thousands of years old. So we've been obsessed with music forever. But why those shapes? And you can see they look like they've been engineered, right? You can see that they've been cut, they've been shaped. They probably did this so that those drums sounded a particular way, or that they sounded pleasing to the ear. So secretly, this was a very mathematical endeavor. Those people were solving spectral problems. All right, there's just such a vast variety of musical instruments out there. And this is, for example, just percussion instruments. If I said the word percussion, what comes to your mind is the dreaded drum set that either you had and your parents didn't like, or your children have and you regret. Yes? But even the percussion instruments, they have these different shapes. You strike them, they make sounds. The sizes are different, the materials are different, but the sounds they produce are very, very different. So what's going on here? Hi, Jacques. There are string instruments. And if you've ever seen any mathematical talk about music and math, there's probably a string instrument. There's probably some figure talking about the fundamental frequency of a stringed instrument and the harmonics, the peaks where the frequencies are most intense. And you might ask yourself, well, how does the length of these strings, how does the thickness of these strings, how does the tension that you change at the very top change the sound? What's going on here? All right. So for example, on the left, there's a picture of the spectrum of a violin A string. You can see that at some points along the x-axis, which is the frequency domain, yeah, does it actually show up? No. All right, so along here is the frequency of the string, and I'll try and explain what that is in a bit. You see that there's these little peaked bits in the graph. The lowest frequency is what we might call the fundamental tone. The next one is a harmonic, and so on. Okay? And by changing the tension in the strings or the density, musicians know that you can change the spectrum or the sounds or the harmonics on a string. What does this have to do with waves? So my pitch is that everything you want to know about math, at least some place intersects with the question of standing waves. So what does this have to do with waves? What I've got here on the right is a little animation showing a sinusoidal wave that's propagating. You can tell that it's going left to right. And that's a traveling wave. And on the left, we've got a wave that's changing amplitude in time, but it doesn't seem to be translating. It's not moving left to right. So a wave that doesn't move left to right or doesn't move in space, its amplitude changes, and the amplitude changes perhaps sinusoidally in time. That's called a standing wave. Okay? And you can actually make a standing wave out of traveling waves. So over here, I've got a wave in green that's traveling to the left, to the right, a wave in blue that's traveling to the left, and all I'm doing is adding the heights at a given point, and I get a red wave. And that red wave, which is a superposition of the green and blue, that one doesn't move to the left or the right. It's just bonking around in place, in situ. So that's a standing wave. So in this little animation, we've got a wave that's moving throughout the domain. It's not stopping, it's not reflecting. But I could create standing waves by taking a room, shutting all the doors, and then bouncing a wave back and forth. That's also allowed. They don't have to travel on and on. I could still create standing waves. So, okay, I think that a lot of mathematics has been driven by music. And for example, way back in 500 BC, Pythagoras decided to describe the relationship between the length of a string and the musical pitch that it produces. Okay. So think about a violin string, right? So you've sort of clamped it, but then the sound you hear, the pitch that you hear, depends on how long the string is. And the statement is that the pitch is inversely proportional to the length of the string. So the shorter the string, the higher the pitch. So the mental image that we have of this business, and this goes back to school, I actually got this figure from my daughter's physics class. So we think about a string that's being held at both ends. And when we think of the violin string business, we think about these standing waves, and they're either like they've got one bump that's moving up and down, or two, or three, and so forth, right? And so when it's got only the one bump, we think about the frequency associated with that as the fundamental tone of the string. And from one end to the other is half the wavelength. Whereas in the middle figure, we've got the first harmonic. You can see a full sinusoidal wave here, and that's the wavelength in that case. So, like loosely, pitch and frequency are kind of the same. Okay? There's a lot more to music theory than I'm letting on, but grosso modo, this is correct. Pitch and frequency are kind of the same. The length of the string is half of the wavelength of the fundamental frequency. The speed of sound and waves, it's about 343 meters per second. And as a very first rough calculation, you want to relate the frequency, the speed, and the wavelength, and there's this triangle that popped up in my daughter's book. Okay, so I looked at this and I was like, what is this triangle? So what this triangle is supposed to tell you is that the speed v is the frequency times the wavelength. I prefer to see it written down like this, but that's okay. That's okay. So if you decided that the v, the velocity or the speed that you're going to put in is the speed of sound waves, well, okay, then all we're playing with is the length of the string, and the length of the string is half the wavelength. So if I had a violin, I kind of know intuitively that the pitch is higher than the bass. So I can look up what the typical bass is tuned to, and the typical bass ranges from E1 to G4. So the lowest tone is kind of like E1, which is about 41.2 hertz. So that's the frequency of the bass string. So let's do this calculation using that triangle shape, right? So the wavelength is the speed, 343 divided by 41. I get a wavelength of about 8.3 meters, which tells me that the length of the bass string is about 4 meters. so I am not 4 meters tall. Admittedly, I don't play the bass, but I think if you had a T-Rex, he could comfortably play this instrument. Okay. So something's gone wrong with the math.
Yeah, trouble with his going.
He's got long hands. They don't look very long, but he does. So this is a very puzzling thing, you might think. So let's go back to the history. So it took almost 1,000 years before Galilei, not Galileo, but Vincenzo Galilei described the fact that on these strings, the pitch is proportional to the square root of the tension. And what's kind of cute about this is, I think this may be the first instance of a natural phenomenon being described by a non-linear relationship. And he was interested in strings. And then about 100 years after, okay, several decades after that, Mersenne used experiments to mathematically model what was going on with strings as you change their thickness. So he realized that the pitch is inversely proportional to the square root of the density. And that might actually help us. So I'm wedded to this expression that the frequency is the speed over the wavelength, and that the wavelength is twice the string length. What changes is what we put in as the speed. We don't put in the speed of sound in air, we put in the speed of sound in the string. And the speed of sound in the string is given by the square root of the tension by the density. And if you plug this all in, and then you look at what the prescribed tensions are on a base and the density of the strings, then you get the E1 as your fundamental harmonic. So now that you've thought about standing waves and you start to poke around a little bit, you realize they're everywhere. So here's an example from quantum mechanics. So the time-dependent Schrodinger equation is over there on the left. And over here is an animation I grabbed from Wikipedia, which shows you on this side the evolution of the wave function. So the red part in blue, the real part in blue and the imaginary part in red of the wave function. And the quantum mechanics magic, if you take the squares of both these waves and you add them and you take the square root, you get a shape like this. And that shape over there, this is something we call the probability density. This tells you the probability of locating a particle along this direction. So wherever you've got a peak, that's where it's most likely to be. So if I were a little particle and I were following this probability density, I'd simply, with high likelihood, I'm kind of bouncing around like that. Yeah. But if you look at, I don't know if I can move that top zoom thing. If you look at the probability density corresponding to this wave or the one above, what you'll see is this stuff is not moving in time, even though the blue and red bits are. So this is a standing wave, actually. Standing waves really, really, truly are everywhere. So they are found in lakes. So you can have something called a siche. It's a standing wave that shows up when you have a body of water over sort of a shallow bed. And if you have air going over the lake, even once the air stops moving, it's excited these waves and these just go up and down and up and down. And if you happen to be unlucky and you've tied your boat to the side of the shore, then it's just going to start bouncing up and down. And sometimes it becomes unmoored. So here's a very cute session. I don't know if this will work. Come on. This is supposed to be a sesh where a river meets the ocean. And what, it's not going to play, but this guy here, this kind of just stays there, just gets up and down. You could try and think about what happens if you take, say, a guitar and then you cut things into it, or you make different shapes with it. And you start to excite standing waves on these shapes, and they will change as you change the shape or you change the material. So this is from a fun paper in 2021. I didn't even know there was a Journal of the Violin Society of America, but you have one. They did these lovely calculations for different shaped boards, I guess. And they plotted the first, the second, the third, and so forth modes of these guitars. They're everywhere in science. So standing waves are used to characterize crystalline materials with defects and inclusions. here you see the frequencies, and where is the peak is where you think of having a standing wave. And as you change from one material to the other, the peaks might change, the locations might change. If you have data and you're trying to separate it, you use something called spectral clustering, which uses the concept of eigenmodes and standing waves. In fact, these objects are everywhere. You could write down a graph of who talks to who communicates with whom, how often they communicate. And then you could try and just use the idea of sending information in periodic waves and see where it concentrates. And that will lead you to be able to tell apart communities in a graph. That's another form of standing waves, but this is on graphs. They can be bad, right? So sometimes you want to avoid these so-called standing waves. So for example, if you have a tokamak, there are certain modes called alpha modes, which if you have them, they cause the plasma inside to sort of start to move away from where you would like it to be. You'd like the plasma to be right in the middle, away from the walls of the tokamak. But if you start to excite too close to one of these terrible standing waves, you can see the plasma kind of starts to escape and then eventually hits the walls, and then the grad student gets fired, and it's a terrible thing. It can be really, really bad. So here's a bridge, and here's a standing wave that you can compute or artistically depict. What you really don't want is to design a structure so that when people are going over it or when the wind's blowing, that you excite a mode like that. That would be bad. A very modern other application is, well, we were in the subway yesterday and this topic came up. The fact that in Montreal, the subways have rubber tires rather than the metal ones. And the reason for that is to reduce noise. Well, why and how does that work? Well, if you have tires and they're going over any surface, could be whatever, a road, then the bumpiness of the road causes things to get excited. And that's going to excite modes inside the tire, which in turn excites modes inside the wheel, and so forth. It just keeps going. And that leads to noise, which we don't like. So we want to make sure to change the materials that we're working with, and also maybe add stuff to damp out these undesirable modes. So at this point, it's a good question to ask, is this even a math talk? Right? So this is like a digression. In Ontario, what they say about applied math is that there's a distinction apparently between applied math and academic math. Applied math enables students to develop an understanding of mathematical concepts, blah, 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 which completely misrepresents anything interesting about math, and certainly does not say very much about applied math. I think math is characterized more by a sense of wonder and curiosity. And it just happens to be quantitative reasoning, but this stuff makes it sound very pedestrian. Rant is over. Sometimes we want to design standing waves just so. So if you had a new stereo and you wanted to figure out where to put it so that when you were sitting in your couch, you got great sound. Well, you would try and find acoustic standing waves. You could try and find the standing waves on the shape of the guitar, as you saw before. But this one is my personal favorite. So have any of you done the cheese experiment before? No? Okay, the cheese experiment is fun. If you have a microwave oven, you take the rotating plate out, and then you stick in a tray with grated cheese, and then you just let it go. So what's going to happen is that the cheese is going to melt, but it's not going to melt evenly. It's going to melt, it's going to have hot spots. And these hot spots are kind of like 2.5 inches, about 6 centimeters apart. So what does this have to do with standing wave? Here's another digression. The guy that invented the microwave oven, he actually realized while working with microwaves that something was melting his candy. And that prompted the whole business of cooking with microwaves. That's a different story for a different day. So let me explain how I might cook with a standing wave. So over here, I've got a device that emits microwave radiation. And the waves come out of here. And if I'm smart, I can put in something that might reflect them back. So I have the waves reflecting back. And if I just keep the distance between them just so, remember, I can have a traveling wave going in one direction, working with a traveling wave going in the other, and I can set up a standing wave. So if I move this wave here just so, I can set it up so that I have standing waves inside the region between whatever is causing the waves to start and the reflector. And it turns out that this is exactly the principle behind a microwave oven and its size. So microwave radiation is about 2.5 gigahertz, which corresponds to a wavelength of about 12.2 centimeters. So what you want to do is you build your microwave ovens so that they're an integer multiple of half the wavelength, because then you're going to get standing waves. And then you can stick the candy in the microwave oven. But when you have standing waves, you've got a region where the energy is really high, and then a region where the energy will never be anything except zero. So it's just a wave that's bouncing up and down in space, but wherever it crosses zero, there's no energy associated to it. And that's going to be wherever you have high energy, you're going to see hot spots. And wherever you have no energy, you're going to see a cold spot. Now, okay, I've simplified the situation a bit. A microwave oven is not a one-dimensional thing. It's actually a cavity. So those standing waves look a little bit more complicated. Maybe if you took a cross-section of a standing wave, it might look like this, where these are the hot spots. So yeah, so the wavelength is about 12. You try and design your microwave to be an integer multiple of 6.5. The nodes are where, the nodes from blue are where things aren't working well. So there's no heating. And then wherever you have the peaks, that's where you have a great deal of heating. And so in the cheese experiment, when you slide in the tray, things are going to melt where it hits a hot spot, right? And if you look at the distance between the hot spots, this is about 6 centimeters, which is not exactly far from lambda over 2, the wavelength of the microwave. So that I thought was kind of. So you can get hotspots in all kinds of different situations. One fun hotspot that Joseph knows a lot about are the hotspots of liquids in containers. So if you're walking with a fluid, then the motion of the top surface, in fact, the motion of the fluid itself, you can think of it as a wave. And sometimes when you're walking, you see that the highest point of the surface, well, it can slosh over your cup. So if you've excited a standing wave, but the highest point of the standing wave was unfortunately close to the edge of the cup. So things are going to spill. And so, for example, if you had a very expensive beverage in a glass like that, the hot spot being near the edge is a very bad thing because it's going to slosh over. Turns out, for a very, very, very expensive beverage like cognac, the shape of the glass is different. And what that does is it makes the hot spot, the highest spot, move a little bit further in away from the edge so things don't slosh out. Again, yeah, so I think it's so interesting that all of this fascinating phenomena occur and they're all related. And it doesn't really at first glance have anything to do with an understanding of mathematical concepts related to algebra and analytic geometry and measurement and geometry. As Quran says, if that's all you learned, like only the boring facts and all, without thinking about melting chocolate, you'd run away from high school. That's what Quran said. All right, so now it's audience participation time. We're going to build a standing wave. Okay, we're going to do this. So I have this little collection of relationships. So I've got the numbers -2, 1, 0, 0. And I'm going to give you some numbers. I'm going to give you the numbers U1, U2, U3, and U4. And you're going to plug it into the first row and tell me what goes into the box. You're going to do the same with the next one and the next one and so forth. Let's just try it. So at first, the numbers I give you, the number U1 is going to be 1. U2 is going to be 3. U3 is, 2, 3, U4 is going to be 4. So if you took these numbers and you plugged it into that grid, you'll get the very first expression here. So what do we get on the very first entry? Do we get, yay! In the next row, we get 1 times 1 minus 2 times 2 plus 3 times 1 plus 0 times 4, which is the next one. Okay, let's keep inducing that. We do the last one. So 0 times 1, 0. What happens here? What do we get? Oh, good. Good. So what I'm going to do is I'm going to take these points and wherever I saw the number 1, I'm just going to put a dot. And then for the number U2, I'm going to put a dot somewhere up there. And U3 was 3, so that's a dot up there. And so, and for the guys on the left, I'm going to put, well, the 0. The next one was 0. The next one was 0. And then I was out here at -5 here. Okay. So rather than deface the CRM and never be invited back, I'll just put this here. So I put in those numbers and the boxes are 0, 0, 0, -5. And the picture looks like this. The numbers I put in, the input vector are in blue. So 1, 2, 3, 4. And then the outputs are here, and I just connected them. And just for fun, I added on 2 numbers, 2 ghost numbers. I'll put a 0 here and a 0 here. Okay? Sure. All good? All right. You did so well. We're going to do this again. So now we're going to put in the numbers 1, 2, 2, and 1. So this stays, this becomes 2, 1. Sorry. 2. Like that. So what do I get now? All right. So yeah. The numbers I put in were 1, 2, 2, 1, and what I got out was 0, -1, -1, and 0. All right. We could make it a little messier. And I would do this by changing the coefficients. So instead of the purple numbers, I'm just going to divide by a quantity h squared throughout for all of them. Okay. Okay, so for all the coefficients get scaled by this quantity 1 over h squared, and h is the quantity 0.2. So I had five yellow dots. This is the point that's x1, x2, x3, x4, and x5 was 1. So I've fixed the endpoints. The ghost points are fixed. I had 5 points equally spaced. The spacing between them is h. Okay? So I've taken the coefficients. I've divided everything by h squared. Anyone want to tell me what happens here? All right. So for a different set of numbers, if I put in, let's say, these points in blue, and I put in more points, just saved you the trouble of doing it. And I computed what I got without the scaling, I'd get the curve in red. But if I did include the scaling, now this time I'll have to divide by a smaller h because I have more points. What I would get is this kind of gets scaled up, so it looks like this. So each of the points in blue is given by the expression xi squared minus xi. And when I've done all the work that I needed to do, I end up with points that are hitting the point 2, and there's a minus sign missing here. Again, the blue and the red curves, they don't really seem to have much to do with each other. I could add more points. Now I've just scaled everything. So if I put in this blue set of points and perform the same kind of procedure, I would get this red curve. I could put in all kinds of blue collections of points and I'll get all kinds of different red curves, except sometimes this happens. I put in the points in blue, and for this very special collection of points, what I get out is this, which has the same shape. In fact, it's just the mirror image of the points in blue. So that's pretty special. And when that happens, we say we have, or at least it looks like a standing wave. So this business of building these tables and coefficients and changing the numbers I put in very elegantly can be encapsulated in the language of linear algebra. So I put the coefficients into a table or a matrix that looks like this. I've got zeros most of the place. I've got -2's on the diagonal and 1's off diagonal. So notice -2, 1, 0, 0, and then -2, -2, -2. So there's this nice pattern. I've just taken that pattern and I've generalized it right here. The inputs are U1, U2, etc. I just collect them into a long, skinny object I call a vector. And then the numbers that come out on the right-hand side, I put them into a different vector. This should be F. So F1, F2, etc. So usually, the way to describe this business I did is to write it in this very succinct form. I take the matrix A, I multiply by the vector U, and I get the output F. But when magic happens, you get AU equals F, but F itself is a constant times U. That's very special. That's when the blue and the red vector are just scaled copies of each other. You could play some games. You could take the number of points to infinity. And then in that case, the number of input values, in some sense, goes to something we called an input function U. Correspondingly, the output vector goes to an output function. And the matrix, in some sense, goes to a second derivative. There should be a minus sign. It goes to minus the second derivative. So the expression AU equals F becomes minus the second derivative of U equals F. There's a minus. And we say that U is a standing wave function when minus the second derivative of U is equal to a constant times U. So that's very, very special. Doesn't happen all the time, not for all input vectors U, but when it does, it's magic. And they're so special, these vectors and functions, that we give them a special name. We call them our own vectors and our own constants. So this constant is called an eigenvalue, our own value. And U is called an eigenvector, our own vector. It's a standing vector. Similarly, for the differential equation, this lambda is called an eigenvalue, and this is an eigenfunction. Any questions so far? Because we're going to... All right. So the words in this business, we've heard the word standing wave, we've heard the word eigenvalue, we've heard the word eigenfunction, we've heard the word spectrum, but these words, so some of these words are of relatively new origin. So Newton coined the word spectrum to describe the spread of light refracted through a prism. So light's being separated into constituent frequency components. And Hilbert coined the word eigenvalue. And he was the first to refer to the set of eigenvalues of a matrix or an operator as a spectrum, which is kind of cool. Not that long ago. So once you see an eigenvalue problem, you start looking for another eigenvalue problem, and they're everywhere. So you could have an eigenvalue problem related to the differential operator's second derivative in X. You could have a coefficient in there. That's a different eigenvalue problem. You could solve something called Laplace's equation or Laplace's eigenvalue problem. You could solve the biharmonic problem. You could study the eigenvalue problems for Maxwell's equations. What I have over there on the screen is eigenmodes of Maxwell's equations in materials where the materials themselves are very weird. So these are anisotropic nanomaterials. You could have eigenvalues and eigenfunctions of the Schrödinger equation. And the eigenvalues for this associated with this problem, the standing waves associated with the time-dependent Schrödinger equation, they satisfy this eigenvalue problem. The notation here is particular. The constant multiplying our function, this is the eigenvalue E. It's interpreted as an energy state. And so if you have discrete constants E for which that equation holds, those are the energy states. And so here are the associated wave functions or the probability density functions for different values of the constant E. And so where you see like a high intensity of the probability density is where you would expect the electron with that energy state to be moving around. So spectral theory is the study of eigenvalues and eigenfunctions for matrices, differential operators, integral operators in physics, chemistry, biology, lots of branches of math. And again, going back to this little history that I had, it started with strings in some sense, but D'Alembert wrote down the 1D wave equation to describe vibrations in a string. So he was thinking about strings as well, right? That's the first PDE in some sense. Then Fourier solved the heat equation, which is related to the one above, but it's not the same. This should be a time derivative, not two. There's a typo there. And he showed actually that in this case, the solution can be written down in terms of the standing waves associated with the equation above. So the wave equation has standing modes, and you can use combinations of standing modes to understand the heat equation, which is kind of cool. Then Poisson in 1826 showed that eigenfunctions for certain operators are actually mutually orthogonal if they belong to different eigenvalues. Sturm showed why nobody should take undergraduate ODEs without thinking about eigenvalues. So this expression right here is why linear algebra is a prerequisite for ODEs. So for this very weird operator here, you can find lambdas, these constants, for which you plug in a phi and out pops a phi still. Okay? Independently and sort of in parallel, Lagrange started to think about eigenvectors of matrices because he was thinking about the moments of inertia. Cauchy started to think about the spectra of real symmetric matrices, which is the hardest thing we ever tell our undergraduates in the linear algebra class, the spectral theorem. Hermite proved the spectral theorem for complex self-adjoint or Hermitian matrices. Then people started to think about integral equations and started to think about, well, what happens with, can you actually come up with eigenmodes or standing waves for integral equations? And this led to, well, the Fredholm theory, which is very cool. So if you're trying to study this equation up here, the integral equation up here, where I give you a g, k is given, it's a function of two variables, and you're trying to find the function v, then solving this problem can be done sort of in an approximate sense by solving this related problem here. You replace integrals by sums. You can write down the determinant for this problem. And then if the function you plugged into the integral was real symmetric, then you actually can show that for certain values of lambda, this expression is zero, which is another fancy way of saying that this equation is an eigenvalue problem for this operator. And so when you start thinking about decomposing a differential operator or the action of a differential operator in terms of standing waves, that's where classical analysis turned into functional analysis. So arguably, we solve eigenvalue problems to understand our world. We do this all the time. We study their mathematical properties. We study the spectra, the collections of eigenvalues for differential and integral operators. We use them to find instabilities because we don't like the instabilities when we're designing fusion reactors. Sometimes we optimize things so that we enhance eigenvalues, and sometimes we design structures to avoid them. Okay? So if you look around this room, the reason there isn't a weird echo in here, and it's not super loud, is look at the materials on the ceilings and on the backs. It's engineered so that you don't have undesirable standing modes for undesirable frequencies. Okay, so concert halls are designed with this sort of stuff in mind. So if you ask me, pretty much all branches of math have a non-empty intersection with spectral theory. It's very rich. Starting from very simple principles, you can get to fairly complex ideas in mathematics. And you can solve all kinds of PDE eigenvalue problems, integral eigenvalue problems. Boundary conditions matter. So This is the one slide for the mathematicians. And this is the end of my talk. Here I have a range of different eigenmodes for different kinds of problems. Your task is to tell me for each of them what the boundary conditions were. So with that, I'll end my talk. So, thank you.
Thank you, Nilima, for this wonderful talk. Now we all wish our students in linear algebra saw this before they start doing eigenvalues. Are there any questions in the audience? Don't be shy.
So the one before last oh yeah, here it is.
Oh, sorry.
The one before last slide, sorry. You mentioned, well, actually you were just mentioning about the acoustics in this hall to not have, you know, very reflective material perhaps and not directly straight. However, when I sing in the shower, I sound much better than when I sing not in the shower. That's subjective. And it is full of glass and very parallel things. So
Right.
what's going on there?
Excellent question. So we like certain frequencies, right? And we don't want to hear certain other frequencies. So if you were to sing in this room and there weren't enough baffling around, you probably won't sound quite as great because the reflections lead to standing waves at a pitch that we don't like to hear. That's the simple answer.
Other questions?
When you were talking about microwaves, I mean, maybe it's a similar question. Basically, when it seemed like the
Cheese.
what's that?
The cheese.
Yeah, the cheese. Basically, my question is, how sensitive are these models to, like, a microwave isn't exactly a cube, and the strings aren't exact, or you know, the things you were showing us as squares are not exactly squares. So if they have, you know, dents and so on, and there's some messy real world object, how much does that change the position of the hot spots and the cool spots and everything?
It can change it by quite a bit. In fact, there was this one fun project I worked on, and I briefly talked about it in my last lecture, where this company wanted to put these so-called metamaterial resonators around a room, but they're expensive. And what they do is, instead of having the walls be reflective for cell phone waves, they kind of make them absorbing. Okay, so you want to know where to place these resonators so that if I spoke, then for certain frequencies, what you heard at that frequency was higher in intensity, so that there was a peak of the standing mode at where you were sitting, right? So just placing a couple of these around the room can actually substantially enhance what you hear. So they've shifted the hot spot from maybe Felix to Jake. So yeah, they can be very sensitive.
The most typical thing is for bass. Where you want to have a hi-fi system and where you put the subwoofer in the room.
Yeah.
It sounds completely different.
Yeah. You can move the couch so that, you know, it sounds good. Yeah.
Oh, I think we have oh, we have one. Okay.
First, thank you for your talk. It was this and the talk on Monday were both very they were wonderful.
Thank you.
I have a question which connects to a bit of what Professor Barnett was talking about yesterday and also Monday's talk.
Yeah.
Which is, if you change the geometry of one of these systems, does the spectra, and you change it smoothly, does the spectra also change smoothly?
Very good question. So you're keeping the boundary conditions the same?
Yes, that's right.
So if you have a smooth domain, right, analytic, and you change it in an analytic manner, then the spectrum changes in a smooth manner. So this is correct. In fact, there was a beautiful series of mini lectures or lectures in the spectral geometry in the cloud series. And it may be recorded, the GEM lectures, yeah. And one of the lectures was precisely about this question. What happens if you perturb things in a smooth way. And then it can be shown that the spectrum changes in an analytic way. However, if I take a smooth domain, think about something like this. Okay, so this is still kind of rounded over here. And then I kind of pinch down. Then all bets are off.
More questions?
I suspect will be from.
Ooh.
I know there are
Yes.
spectral surfaces.
Right.
Are they? We don't know.
We don't know. It's a great question. We should have a thematic semester on this very hard open problem. So I've got one surface for which I know the spectrum. I want to create another surface which has exactly the same spectrum. And so find a way to go from this one shape to the other shape without changing the spectrum. It's hard to do. If you give me a finite number of eigenvalues, you can design a shape that has that finite number, but the rest of the spectrum is whatever numbers. It's hard to match everyone. Kind of like taking a family on a picnic. It's hard to keep everyone happy. Match nothing.
More questions? Oh, sorry.
Ben had a question? No, no, sorry.
I
No.
was just going to follow that and ask, do you even know that there are infinitely many shapes that have the same spectrum?
No.
Yeah.
But then it's not rigidity. Let's say if you have, I don't know, some.
Well, the negative curvature.
No,
that's the
negative
data.
curvature.
The negative curvature, that is a result based. Dealing on the cash down.
Yeah.
But generically for generic operators, no.
Yeah.
Generically, it's not.
More questions? Maybe I can ask one. So you showed a definition of applied math.
No, it's definition.
No, it wasn't definite. It was like things that
What people say.
what people say.
applied math is.
Exactly.
Yeah.
Yeah.
In Ontario. It's of course it's just.
So you showed us the thing that you don't like.
Yes.
What would you replace it with if you
I'm going to channel Doug Arnold and say, don't ever let anyone pin you down to define applied math. Yeah.
Okay.
People wrote that and have it replaced by chat.
Excellent. Excellent. Excellent.
Any other questions?
Well, you haven't answered mine. So in these shapes, what's the boundary conditions say? So these are, this is the fundamental mode, the higher mode, and so forth. What are the boundary conditions on this guy or any of these? Can you tell?
Sure. Yeah, they changed. It's originally on the right hand side and Neumann on the left hand side. It's like, but it must changes over something.
Yeah. So there's these jumps over here. So that's Dirichlet here, Neumann here. Yeah. And what about this guy? Does this look like it's got a changing boundary condition? Loser buys me a beer, so. Okay. No, you're right. This one doesn't change. That one's clearly clamped, so that's Dirichlet all around. And that one's a little bit harder. All right. Well, that's it from me. Thank you.
Thank you very much. Thanks again, Nilima, for this wonderful.